In the case of nucleophilic addition, we've been talking about systems that are reversible, either under basic or acidic conditions. Well, there's another class of nucleophilic addition reactions that happen under neutral conditions, and we want to talk about those now. The first class are the imine and enamine formation reactions. Now, these reactions are similar in mechanism to the acetal formation, but they form under neutral conditions. Like acetal formation, water must be a leaving group, and while this is not possible under basic conditions, strongly conditions will just protonate the amine, leaving the reaction dead. So in imine formation, what happens is we get nucleophilic attack onto a carbonyl by an amine. Right? So we can't have acidic conditions here because it will just protonate the amine and leave it dead. But under neutral conditions, what happens is the nucleophile adds to the carbonyl, and we get a tetrahedral intermediate. And we get some sort of proton transfer event happening to generate a species known as the hemiaminal. So this species, the hemiaminal, kind of looks a lot like the hemiacetal. And so we have an ability here to eliminate water by stripping away the H2O that's embedded within this molecule. And so the way this does that is through use of the nitrogen lone pairs. And so what happens here is the nitrogen lone pairs help to promote the loss of water by moving to form a double bond. And then what happens is that the oxygen carbon bond grabs the proton, and then the hydrogen nitrogen bond breaks to form a lone pair back up onto nitrogen. And so we're losing water in the process, and then what we get is two molecules that are E and Z isomers of one another, known as the imines. And so these are E and Z isomers, and together they're functional groups known as imines. So this is usually run at around pH 4 or 6. Acetic acid is normally added as a catalyst, and this is a weak acid. Several different types of amines can be used, however, and those products of those reactions have special names. So in each of the cases that I'm going to write next, the amine is a primary amine and water is removed. And we call these reactions condensation reactions because we're losing water. But the mechanism is still, the same, addition to the pi star CO. And so the several types of named species that we have here are as follows. So let's say we have a ketone or aldehyde in the presence of hydroxylamine. Okay, so in the presence of hydroxylamine, where R double prime is equal to H, we're going to get a product molecule that incorporates this functional group in there. And this is an imine, but this imine has a special name. It's called an oxime. When we take a ketone or aldehyde and we react it in the presence of a hydrazine, so this is hydrazine, where R double prime is equal to H again, we get a product molecule known as a hydrazone. And the last case is when we take a ketone or aldehyde in the presence of a molecule called a semicarbazide. So semicarbazide would look like this. And the product that we get is called a semicarbazone. And so all of these reactions are a class of reactions known as condensation reactions, or really what they are imine or enamine formation that are nucleophilic addition to the carbonyl under neutral or slightly weakly acidic conditions. Now, when a secondary amine is used instead of a primary amine, we get a different product. So let's take a look at that now. So let's say we start with this ketone, and this ketone has what we call alpha protons, right? So at this alpha position here, we have two alpha H's, right? Two alpha protons. And when we treat this with a secondary amine, let's say we're going to treat this with pyrrolidine, what happens is we still get nucleophilic addition to the carbonyl. And so let's draw that out. We get a proton transfer event happening to give us our hemiaminal species. And so here's the hemiaminal. Sometimes you'll see this called a carbinolamine. And then what happens is we get loss of the OH, and we get this loss of OH by taking the lone pairs on nitrogen and helping to kick it out. So this is one of the rare exceptions to the rule that OH is not a good leaving group. We have a good leaving group here. We have a loss of the OH here because it's being helped by the nitrogen lone pairs. And it creates this species known as an Iminium Ion. This is not an imine because it's not a neutral species, it's an Iminium Ion. And this Iminium Ion is still reactive, and so what can happen here is that the OH minus that was the good leaving group is going to come back in and remember those alpha protons, it's going to actually deprotonate those alpha protons. And as it deprotonates those alpha protons, it's going to take the CH bond and move it in to form a double bond, and then the lone pairs are going to go up onto nitrogen as, the double bond is going to go up onto nitrogen as a lone pair. And so what we have is a series of isomers at this position, and these are known as the enamines. Right, so ene meaning alkene, and amine meaning you have a nitrogen in there. And again, it's a mixture of E and Z isomers. And so the resulting iminium ion deprotonates to form this enamine. And the most common secondary amines that are used to form these enamines are things like pyrrolidine, things like piperidine, and things like morpholine. These are the most common ones, and I'll write those out. So this is pyrrolidine, piperidine, and morpholine. Some sort of dialkylamines also work, so you can also take things like dimethylamine, something like that. You can take asymmetric types of dialkylamine, so methylethylamine. But in order for enamine formation to proceed, again, you have to have these alpha protons. That's a requirement for these reactions. Now, we're going to come back to the use of enamines a little bit later, but I want to take a little bit of a detour on the use of imines in synthesis. And I want to kind of go back to a little bit of first semester chemistry. And that's our sort of discussion of SN1 and SN2. And so let's take a look at the problem here. If I have methylamine and I react this methylamine with methyl iodide, okay, I know that I can get an SN2 reaction. I can get the lone pairs on the nitrogen to attack the methyl group to give me a displacement reaction, and so I'm going to get an SN2 reaction, and I'm going to get as a product here methylamine plus a molecule of HI. Now this is a standard reaction that we can draw with our arrows, but the problem is when you run this reaction in the laboratory, that's not the product you get. What you get is a continuous reaction. You get this reaction to go again and again. And so the reaction doesn't stop at just the mono substitution. And so what we're going to get here is the trialkyl amine plus HI. And in some cases, if you force this and heat it up, you can actually even get the ammonium ion. Right? So trimethyl ammonium salt. So the question here is why is this happening? This is happening because your starter material, your product, is more reactive than your starter material. Now, why is that the case? Well, recall our discussion of hyperconjugation. And so we have a system in which you've got a nitrogen here, and we've got methyl groups hanging off of that nitrogen. And let's say we have another one here. Okay. What's happening is that as you substitute more and more, you're going to get those CH bonds are going to be able to overlap with the rest of the system. They're going to basically push electron density towards something that already has a lone pair. And so this is sigma donation or hyperconjugation, in which you're going to increase the energy of that lone pair. And so what's happening is as you get more and more sigma donation, the energy of your non-bonding pair of electrons on oxygen or on nitrogen is going to increase. So your HOMO is going to increase. Right? So sigma donation leads to an increase in the energy of the non-bonding pair of electrons on nitrogen. And so this is a problem, right? Because of hyperconjugation, it's very difficult to stop the reaction of a primary amine with an alkyl halide at the monoalkylation, right? The reaction just keeps going because the product is more reactive than the starter material. So there is a way to circumvent this problem, and that's to use the imine functional group as a good handle, right? So we're going to go over the reaction that does circumvent this, and this is known as a reductive amination. Okay, a reductive amination of a ketone or aldehyde is when we react a primary amine with a ketone or aldehyde to give an imine, but then we reduce the imine with a reducing agent in situ. Okay, so here's how it works. So let's say we have this ketone here. And we take this ketone and react it with this aniline. Okay. Now we could form an imine in the process, And we would take this imine, and then we would need to reduce it with a reagent like sodium borohydride. But that process would take 2 steps, right? But we could potentially do it in a single step, right? And so we would need a reducing agent that wouldn't be able to reduce the ketone, but that would be able to reduce the resulting imine. And so we do this by tempering the reactivity of sodium borohydride. And so we use something known as sodium cyanoborohydride instead. Okay, so let's take a look at this reaction. And so I'm going to show the product of this reaction. This reaction gives us the reductive amination product. Okay, so let's do the first thing. The first thing is that we're going to form an amine. And so we're going to take the nitrogen lone pairs on nitrogen, attack the sigma star CO, and we're going to get this product, which then is going to undergo a proton transfer to give us the hemiaminal. And that hemiaminal is going to give you the imine like such. Okay? Now what can happen now is that you can get sodium cyanoborohydride to react with that imine. And so we've got a borohydride reagent that is less reactive and more selective than sodium borohydride is. And so what happens is it doesn't react with the ketone. So sodium borohydride would react with the ketone, and so we can't use sodium borohydride in this reaction. But what we can use is sodium cyanoborohydride, or we can use another one called sodium triacetoxy borohydride. Okay, you can also use this one. And these reagents will not reduce the ketone, but they are reactive enough to reduce the imine formed in situ. Right? So what happens is that the borohydride comes along now, and it can reduce the imine. And so what you get is an addition of a hydride to that center. And then finally, you get methanol becomes your source of a proton. It protonates that that imine, and then you have your product. Right? So this particular step, of course, is irreversible, right? Because we're using a hydride source. But this allows you to generate an amine, a secondary amine, without further addition of more and more substituents. Right? So this gets around the problem of over-alkylation. Okay, there's another type of reaction that can proceed under neutral conditions, and that's the Wittig reaction. So we've been talking about imines and enamines, but there's another type of reaction known as the Wittig reaction, which involves the element right below nitrogen on the periodic table, and that's phosphorus. So one important reaction in organic chemistry is the reaction of a ketone or an aldehyde in the presence of what's known as a phosphorus ylide. And so let me draw out this reaction first. So if you take a ketone or aldehyde, and then you take a phosphorus ylide, which is this species here, and an ylide is just a system which have charges on adjacent atoms. what happens is you get a mixture of alkenes. Plus triphenylphosphine oxide. Okay, so this is known as a Wittig olefination reaction, or a Wittig reaction. You're forming an olefin. An olefin is just a fancy name for an alkene. Now, the formation of this ylide occurs by SN2 chemistry and then deprotonation. So we can form ylides very easily by just taking let's say an alkyl bromide, taking this reaction and taking this reagent and reacting it with triphenylphosphine. And so what happens is we get phosphorus attacks the carbon via an SN2 reaction, right? And then we get this species. But then we can have a deprotonation event. And so what normally happens is we use a base such as potassium terbutoxide, but you could also use something like sodium hydride or LDA or even N-butyllithium if you want to do something a little bit stronger. And so the base will then eventually deprotonate that position, and the electrons will move up onto that carbon atom as a lone pair. And so essentially what you have is a negatively charged species right next to a positively charged species. And we often draw that actually in its form in which we have a double bond in between those two atoms. And so we call this an ylide. And it has, double bond character. And that's because phosphorus is, of course, on the second row of the periodic table, and so it has those extra d orbitals. Now, the treatment of these ylides with ketone or aldehyde results in a nucleophilic addition. And so let's draw that out. And so we can take this ketone, and we're going to react it in a reversible reaction with the ylide. And so we have this ylide here. We can have the nucleophilic part, the negative charge on carbon, react with the carbonyl carbon, the pi star CO. And what that's going to do is it's going to generate what's known as a betaine intermediate. And so I've got this negatively charged species on oxygen. I've got positive charge on phosphorus, and then I have my R groups. And so this is known as the betaine intermediate. And this betaine intermediate can go in the reverse direction. It can spit out the ylide and the ketone, right? So this is under thermodynamic control. But if you want to proceed forward, you can get attack of the oxygen atom onto the phosphorus. And so when that occurs, you get a cyclic species. And this cyclic species is known as a cyclooxyphosphate. And so this cyclooxyphosphate is pretty stable, but what can happen in order to get product is you get a reaction known as a cycloreversion. Now, cycloreversion is really simply a retro 2+2 reaction. And so what's going to happen is you're going to form a phosphorus oxygen double bond at the same time as forming a carbon-carbon double bond. And so what you're going to get here is a product that looks like this, in which you've got a mixture of isomers, of course, but you've got a new double bond forming. In the process, you're going to generate a triphenylphosphine oxide, And remember that triphenylphosphine oxide is one of the most stable compounds in all organic chemistry. The phosphorus-oxygen double bond is really, really strong bond. And so this reaction is kind of pseudo-irreversible. It's not really going to go in the reverse direction. Okay? Okay, so there's a little bit of debate about this mechanism, whether or not this betaine intermediate actually exists. And so an alternative mechanism has been proposed, and that's the one in which there's a direct 2+ addition. And so let's talk about that for a second. So if we have our ketone, and we're going to react that ketone with the betaine, but this, the phosphorus ylide. But this time I'm going to draw this phosphorus ylide with its double bond intact. And I'm going to say that this reaction is going to undergo a 2+2 cycloaddition. And the 2+2 is going to involve formation of a oxygen-phosphorus single bond at the same time as forming a carbon-carbon single bond. And so this is a different way of getting that cyclooxyphosphatane intermediate. And so this cyclooxyphosphatane intermediate can then undergo the cycloreversion, the retro 2+2, as drawn here, and you get the same set of products. So it's really that first step that's the one that is a little bit of a debate in the organic chemistry literature. All right, so we get triphenylphosphine oxide, of course, as our byproduct, and this reaction is complete. It's not going in the reverse direction. Now, notice that there's a mixture of E and Z isomers in each of these mechanisms. So this is common between whether or not you're going through the betaine intermediate or doing the direct 2+2. So we have to consider stereochemistry in this reaction. And so there are a couple of rules. A general rule is that stabilized ylides will give you E alkenes. All right. So how do we describe a stabilized ylide? So an ylide may be potentially one that has an electron withdrawing group on it. So let's say we have an ylide here in which we've got a triphenylphosphine, but that triphenylphosphine, this phosphorus ylide has negative charge directly in conjugation with that ester group. So this would be an example of a stabilized ylide. And so if you were to react this with an aldehyde, for example, you would give the E alkene. And that's because that first step, that betaine intermediate or the 2+2, is a reversible step. All right? And so you're always going to be able to funnel into the more stable of the two products. Unstabilized ylides will give you the Z alkenes. Okay, and so an example of this would be this one, in which we've just got let's say an alkyl group on there, so maybe like a isopropyl group or something. All right, and so this is not a stabilized ylide because we don't have a way to stabilize that negative charge. And so this is going to make the attack onto the carbonyl irreversible, right? And so an irreversible addition is going to favor the lower energy transition state, which happens to be the one in which the two groups are on the same side, and so you're under kinetic control. And so in the case of stabilized ylides, you're under thermodynamic control. And in the case of unstabilized ylides, you're under kinetic control. And so you get the Z product in which the two groups are on the same side.